So first of all, Happy New Year to all of you, and welcome to this third seminar of the student series. I think it's the fifth or the sixth that we have done since September. And as you see from the title, what we have today is an overview on Attosecond science. And this comes perfectly on time because you know that this year the Nobel Prize is being given to 3 scientists working in this field, in Attosecond science, to Pierre Agostini, Anguier, and Fernando. So we have today Fernando Martín, who's catedrático from the Department of Chemistry of this university, and he's also a scientific director of the Nanoscience Institute, where I also work. And we have, we are lucky to have him because he's really an expert in the development of computational methods to study light and matter interactions. Particularly, he's been pioneering methods for electron dynamics and to interpret experiments with attosecond pulses. So I think he's going to focus today a little bit about not only the field itself, but also probably the expectations for the applications in the future. So for those that don't know Fernando is an eminence in the field. He has many prizes. I will just cite 3. He received the Premio Nacional de Investigación Rey Juan Carlos I, Premio Rey Jaume I of Research, Fundamental Research, and the Miguel Catalán Medal given by the Spanish Physical and Atomic and Molecular Physics Society. He's been also recipient of the ERC grant a couple of times, and is really probably he's the main person to talk with more authority to talk in this field here in Spain. So we are very happy that he offers himself to give the presentation. So that's it. Thank you very much, Fernando. And the floor is yours.
Well, thank you very much for the introduction. It's too exaggerated, I could say. But thank you very much anyway. So I want to thank Juan and Juan Carlos for inviting me to this series of seminars that is becoming so popular in the Faculty of Science nowadays. So yes, as Juan said, I will speak about Attosecond science. So the talk will have a part that is very general for those who do not know anything about Attosecond science, and then there will be some more real scientific stuff towards the end of the talk. So as Juan said, well, this is very timely because in last October, I think, these 3 people got the Nobel Prize for experimental methods that generate attosecond pulses of light. So the word experimental is critical here. Is 3 experimentalists who got it. And so attoseconds. What is an attosecond? Well, an attosecond is 10 to the minus 18 seconds. And this is to a second what a second is to twice the age of the universe. So that means that the second, for practical purposes, is like infinite time when we are looking at processes occurring in the attosecond time scale. So my talk will take around 10 to the 21 attoseconds, okay? Just to inform you in this new scale how things look like. Now, why should we care about attoseconds? Well, because this is the typical time scale in which electrons move. So, for instance, you go to your textbooks about the Bohr's model of the hydrogen atom and calculate how long the electron takes to go around the proton in the first orbit. Well, you can do it very simple. It takes 150 attoseconds. So that means if you want to see how the electrons move in real time, you have to access this time scale. That's why the development of attosecond pulses is so important. And this motion is much faster than any other motion occurring in the molecule, like, for instance, molecular vibrations that typically occur in the femtosecond time scale, or rotations, or molecular dissociations, or chemical reactions. So the program for the next 10 to the 21 attoseconds is the following. So basically, I will review very briefly why these people got the Nobel Prize. I think it's important because there are some messages there that you can learn, especially when you are starting your scientific career. And I will describe briefly the publications that led them to get the Nobel Prize, and then I will illustrate what they mean in simple terms, so that I think everybody can understand. And finally, I will describe the current status of the field and where the field is going. So the story starts in 1975 when Pierre Agostini published this paper in Physical Review Letters. And basically, before this paper was published, what people knew is that if you wanted to ionize an atom or a molecule or whatever with infrared light, of course you need several infrared photons to ionize it because the photon energy is much smaller than the ionization potential. This was known, this was possible. But then when the intensity of the lasers increased, they realized that the system could absorb more photons than needed to be ionized. So there were photons that were absorbed by the electron that was already ejected in the continuum. And this process was called above threshold ionization. And it was a kind of surprise because nobody was expecting it. And the reason why this happens is because the intensity of the lasers in those days increased dramatically, and then this is the reason why you can absorb more photons than needed. Something that was known at that time was the fact that when the system absorbs several photons at the same time, well, we have seen that these photons can lead to emission of electrons. But what can happen also is that these photons can recombine in a single photon that is emitted. So for instance, in this example, we have the absorption of 3 photons to simplify the picture. And then these 3 photons recombine and to see the emission of light that has a frequency that is 3 times the frequency of the laser you use. And this process is called harmonic generation. This was known in this period, and to do it, what you need is an intense infrared pulse. Now, what is the efficiency of the process? Well, the efficiency is very low. This is gives you more or less the efficiency, which is this is the efficiency for the case in which you absorb only 1 photon, when you absorb 2, when you absorb 3, etc., etc. And what is important here to realize is that the coefficients that multiply these terms decrease very rapidly. So you see that the efficiency of absorbing 2 photons and emitting a photon with twice the frequency of this photon is more than 10 orders of magnitude smaller. Okay, and if you have to absorb 3 and you combine the 3 photons, then it's more than 20 orders of magnitude. So the efficiency of this process is very low, very low. It decreases with the number of photons that recombine to generate the harmonics. In this context, I'm really perform an experiment just to see this, to see the harmonics. This was like 10 years later. So what she did was just indeed to see this process. So she irradiated this, I think it's argon, and then she observed that 3 photons recombined led to the emission of a bigger photon with 3 times the frequency, and with some efficiency. Let's say 1. Okay, it's normalized to 1. Now, what you will see here in this figure is, the efficiency of this harmonic emission as a function of the number of photons that recombine. Then what she saw is that, as one could expect, recombining 5 is much less efficient. Recombining 7 is even less efficient. So nothing surprising. And if you are a well-trained scientist with certain age, you would say, well, it's not worth going beyond that because I know what is going to happen. It's going to decrease forever, and then at some point I will see nothing. But if you are a young researcher with no contamination from a prioristic ideas, you say, well, anyway, I want to go further and look at this region. And this is what she observed. Suddenly, these stopped decreasing, remained more or less constant for some time until it decreased again. And look, this happens in a wide region of photon energies. So there is a plateau, a cutoff, and the important thing is that this plateau corresponds to emission of photons in the extreme ultraviolet. So the process is you shine infrared light in the system and you recover extreme ultraviolet light. That's why it was called high harmonic emission. Okay. So this was the unexpected discovery that was published in Journal of Physics B, not in Nature or Science or whatever fancy journal. Journal of Physics B, nowadays impact factor 2. She got the Nobel Prize for this paper. I wanted to mention this just, I think it's a good message. Then the question is how this light is emitted. Nobody knew. They saw the light, but they didn't understand in which form was emitted. So Pier Agostini, again, much later, 2001, performed an experiment in which he showed that the light was not emitted in a continuous way. It was emitted in bursts of light, of light during some attoseconds. So basically, what happens is there is a pulse of light that is emitted in the XUV, then nothing is emitted, then another pulse of light with the same duration is emitted, then nothing, and so on. So it was a train of attosecond pulses. So this XUV light that is generated is not emitted continuously, it's emitted in the form of a train of attosecond pulses. And this was the discovery by Pier Agostini. Still, it was necessary to check that this was indeed an attosecond pulse of light. All of this was indirect evidence. And so the final proof that this was indeed a pulse of light of attosecond duration was provided by two papers by Fernando, also around the same time as Agostini's experiment. So what they did in these experiments, basically, they said, okay, let's take one of these attosecond pulses that still we don't know how they look like, and let's use them to see something that takes longer, that takes more time. Okay, so let's use it to take pictures of something that's, at longer time scale. If we are able to resolve this in time, that means that we indeed have attosecond pulses. And this is what he did. He used this to visualize another pulse of light, in this case an infrared, much longer. Okay? So he varied the delay between these two pulses and took pictures of these longer pulses at different times. And this is the experimental result, where indeed he could see the oscillations of these longer infrared pulse with a resolution that is of the order of attoseconds. So it resolves perfectly the oscillation. So this is basically why these people got the Nobel Prize. And as you can see, this is work that was finished basically at the beginning of this millennium. Okay, so they got the Nobel Prize more than 20 years later. So why this light is emitted in the form of pulses? Well, of course, there's a lot of theory behind that, but I will give you a very simple picture. So let's take, for instance, an atom with only one electron, sitting in this, energy level. And now let's shine one of these intense infrared pulses into the system. Now, if you use elementary electromagnetism, then you can calculate the potential, the additional potential the electron will experience when you shine with the infrared pulse. And this is given, of course, by the position of the particle, or the electron in this particular case, the charge, and the electric field. In this case, the electric field that the electron feels is given by this simple formula. This is just a simple equation to understand the physics. But this describes, of course, something that oscillates in time, this is the wave, with an envelope f of t that limits the duration of this oscillation. So this is the typical infrared femtosecond pulse. So the potential, the additional potential you have here, is proportional to x, to the position of the electron. That is very important. It oscillates with frequency omega, the frequency of this infrared pulse, and is proportional to the amplitude of the electric field. And the amplitude of the electric field, the square of the amplitude of the electric field, is proportional to the intensity of the laser. So you have a very intense laser. E0 is a very large number, which means that this potential can be even higher than the potential the electron feels in the presence of the nucleus. Then when you add this potential to the normal one the electron feels in the atom, knowing that E0 is very large and that this term is proportional to x, then you realize immediately that as a function of x, this is a straight line with a slope given by this. And this slope is proportional to E0, so it's a big slope, and it oscillates with omega. So it can be positive, negative, it will oscillate. So the actual potential the electron feels in the presence of the infrared pulse is this one. This is just one cycle of this infrared pulse, and then you see that this potential oscillates because there is this straight line that superimposes to the atomic potential. And then you can see that if the slope is very big, then the electron can escape. There is no more potential barrier, so the electron can go. So in fact, what happens is this is more clear, I think. This is in 2 dimensions. Then you see the atomic potential, then you see how this potential oscillates. The yellow balls are the electrons. And then what you can see is that when the slope is very big, an electron can roll down, and then when it comes back, it can go back to the initial position. Most of the electrons will be ejected and will never recombine with the atomic nucleus. But some of them can be captured by the nucleus again if they remove all the kinetic energy they acquired during this round trip. So the electron is ejected because there's no more potential barrier. It can escape. It will be accelerated because it rolls down the slope. Then it comes back with a lot of kinetic energy. And then if the electron is able to lose this kinetic energy in the vicinity of the nucleus, then it will be recaptured. And how the electron can remove this excess of energy? By ejecting an exubit photon. So that's the reason why you see that exubit light is emitted, and you understand also why it's only emitted when the electron recombines. So if the period of this oscillation is the period of the infrared pulse, let's say is 1.5 femtoseconds, this is the typical period of infrared light, that means that the light will be emitted during a time that is much, much shorter than 1.5 femtoseconds. That's why the light that is emitted is only emitted during a few attoseconds. And it's emitted with the frequency of the infrared light because, there is always an electron that can go and come back, and then when the new cycle starts, the electron can repeat exactly the same thing. And so you are producing the train of attosecond pulses. Now, I hope you understood why this light is emitted in this way. This is very important because attosecond pulses of light have special characteristics. And to understand these characteristics, let me go to the simple case in which you have monochromatic light. Monochromatic light means that you have a frequency, well-defined frequency or a well-defined wavelength, and then it contains a single color. Now you have an attosecond pulse. Of course, you only have oscillations during a very short interval. You Fourier transform this, then you end up with something like that, which tells you that the light that is contained in one of these attosecond pulses is not monochromatic. You have a lot of different colors in it. Okay, there is not a single frequency here. You have an interval of frequencies that are contained in the pulse, and the width of this distribution can be rather large. In this case, I have here a pulse of 1 femtosecond, so it's not even an attosecond pulse. And you see that the width of this is around 10 electron volts. 10 electron volts is comparable to the ionization potential of any molecule of atom. Okay, so it's very wide. If you reduce the duration here, for instance, 500 attoseconds, which is half of this, you will have 20 electron volts as bandwidth, as the width of this distribution. So the light you have is not monochromatic at all. You have many colors, but all these colors are in the X-UV. That is important. Now, with X-UV light, you can ionize anything. An atom, a molecule, a material. You shine this light, and there are electrons staying. For instance, this is the typical diagram of energies of molecular orbitals of a molecule, with a typical ionization potential of around 10 electron volts. You can, with X-UV light, of course, you can ionize the molecule from any molecular orbital. Any. You have enough photon energy to do it. But there is something interesting here, is that you can do it by using photons of different energy, because you have those energies in your pulse. So, for instance, what you can have is that you can ionize, let's say, from the upper valence orbitals, with a photon with the smallest energy contained in the pulse. Or you can ionize it from inner valence orbitals by using a photon with much higher frequency. Those photons are in the pulse, both of them. But it can be that, because of that, the energy of the electron, when it is ionized, is exactly the same. And what does it mean? This means that if I ask you, by looking at the electron energy, where the electron came from, you cannot tell me. And this means that, indeed, what you have is a coherent superposition of electronic states, or in other words, an electronic packet. So what you are producing with attosecond pulses when you ionize the system is a coherent superposition of electronic states. And the coefficients of these coherent superpositions are given by the ionization amplitudes. So you want to describe this theoretically, you have to describe ionization. Otherwise, you cannot describe this electronic packet. And this is completely different to what happens when you have more normal light. Let's say light, perfectly monochromatic, or very long pulses of light. Very long, for instance, nanoseconds, or even longer than that. Because in that case, you know, the light is perfectly monochromatic, so you don't have photons of different energies. You have photons of a very well precise energy. So if you remove the electrons, let's say from here or from there, it makes a big difference. The photon energy is exactly the same, so the electron takes a different kinetic energy in these two different situations. So if I ask you now, by looking at the electron energy, where the electron came from, you can tell me. So this is a big difference. No coherent superposition of states. Okay, so this is, let's say, the introduction, the general introduction of the field. And now the key question is, okay, these people got the Nobel Prize, but this is worth for something or not? And this is where other people have been working, including, for instance, people in my group, for the last 15, almost 20 years, to see if these things can be applied to something, to do something. And there are basically three important research topics in which people are working. One is attosecond chemistry, that aims at imaging and controlling electron dynamics in molecules, not to do new chemistry. People are using these to condense matter, just to control electronic currents in semiconductors, topological materials, etc., etc. All that has to do with electronic motion, you know, is worth studying with attosecond pulses. And more recently, people are trying to use this in the context of quantum technologies as a new way of inducing an entanglement and controlling it. And now you understand why, because I said with attosecond pulses, you produce coherent superposition of states, entangled states. So it's possibly an alternative to other entanglement schemes in the market to produce better entanglement or more efficient. Well, in the rest of the talk, I will exclusively concentrate on attosecond chemistry, which is the field in which my group is working. And it's also the topic of one of the European network that is operating nowadays with this Attosecond. Okay, so there is a lot of people involved in this research, not only us. So the very first thing you would like to do with your Attosecond pulses is to use them to see in real time how the electrons move. So to record a movie. So let me recall you how you make a movie. Movie is just the projection of a sequence of different frames obtained at different times. And you project them one after the other so that you get the illusion of motion. Okay? Now, for the movie to be properly done, you have to take care of two things. One is that the frame exposure time must be shorter than the typical time the object needs to move significantly. If you use a too long time, then the picture is fuzzy. So you need short time. And short depends on how long the object needs to move significantly. The other important concept is that the time between consecutive frames must be short enough. For instance, in this super slow motion picture of a water drop, then if you want to see all these tiny details, then you have to take many frames in a given time interval. So the time interval between consecutive frames must be very, very small, much smaller than the time these little drops need to move significantly. So these concepts are exactly the same when you want to do a movie in the Attosecond time scale. The only problem is that both the frame exposure time and the time between consecutive frames must be of the order of the Attosecond. So how do you do a movie? Well, this idea is not new. It doesn't come from the Attosecond science field. It comes from femtochemistry, in fact. Is to do a pump probe experiment. The difference with femtochemistry is that the pulses that are involved here have attosecond duration. So basically what you can do is use one of these attosecond pulses to shine a molecule. Then there will be electrons going out, as we say, because these you have energy to ionize it. Then you will create a hole, and there will be some electron dynamics going on after that. And then you want to take a picture of these electron dynamics at consecutive times. How do you take the picture? You come with a second pulse, I take the picture, and then you may see a hole here. You come with the same pulse later on, and take another picture. Then you may see that the hole has changed. And so on. So in this way you record different frames, and when you project them one after the other one, in principle, you should see the motion of this hole in the model. Of course, the pictures are not as nice as these ones I'm showing here. This is an idealization, but the concept is this one. So what I'm going to do now is to show you the first movie ever recorded in a model of how electrons move. This was published in 2010 by the group of Malraki, Mauro Nisoli, and we were in charge of doing all the theoretical modeling just to understand this. And this followed exactly the pump probe scheme I have described. Okay. And well, you see some names here with some squares. This is because I'm reciting this from the Nobel Symposium meeting that took place in August, 3 months before the Nobel Prize was awarded, in which I had to present these things just to highlight how important Attosecond science was in order to award the Nobel Prize. Okay. And all these people were present. Among them, and me. So here is the movie. I stop here because it's important you concentrate and look at it carefully. I put it in. So you laugh, but I don't know why. You should be impressed by this. Of course, you laugh because you don't understand anything. So let me just expand it and put the frames one after the other one, in the way you would do with a normal movie. So you put the movies one after the frames one after the other one, and then there's just the frame that's the nothing else. But this movie is super important. It's the equivalent of the first movie that was ever produced in real cinema. This is the famous movie of the train arriving to Saint-Lazare station in Paris, produced by the Lumiere brothers, and you have read this internet. Well, you see that people stood up and ran away because they were scared of the train running into them. You didn't do that, yes. And why you didn't do that? You didn't do it because you didn't understand anything. It's as when you go to a 3D movie theater to see one of these movies, you need glasses. If you don't have glasses, you don't understand the movie. For instance, this lady has problems to understand what is going on in the movie. Okay, and in fact, you are creative enough to make them think that it's exactly this. So why you don't understand anything here? Because you need glasses, and the glasses come from free. So we are glass producers. So to produce these glasses, we have to solve some equations. Basically, the equation one has to solve is this one, the time dependence on the equation. Why we need this? Because we need quantum mechanics. I'm talking about electronic coherences. So quantum mechanics. No escape to this. I'm talking about the electrons that escape from the molecule. So ionization. So electrons that are not bound. Forget about quantum chemistry. You also have nuclei moving. The nuclei are there all the time. You should not forget them. And they move slowly, but they move. And we want to see things in time domain, so we need time. So this is the question we have to solve. And to solve it, there are no standard methods. One has to develop your own methods. I will not describe them because it will be too complicated, but you are interested in knowing about those methods, I can tell you. So let's go back now to the same experiment, to the first one, now with the glasses that we developed. Let's look at the movie again. Probably you will not laugh anymore. Here's the result of this experiment. This is time, okay? And here you see the some bands of different colors. Basically, what these bands are telling us is where the electron is. When you ionize the molecule, there is one electron remaining in the H2 plus molecular ion. Okay, but as we know, this electron should move from one side to the other one. This is what we are told at the elementary school. So the colors here indicate, the change of colors here from blue to red and so on, indicate where the electron is. If it is red, it is on the left. If it is blue, it is on the right. And as you can see here, the electron moves from left to right in periods of around 1 temperature. So, and why we are able to say that? Because the theory allowed us to go backwards and understand that this is exactly what was being produced. So, what this image is telling us is how an electron moves in the presence of two nuclei. So it's the movie of the localized motion of an electron in a covalent bond. So there is absolutely nothing new here. We knew that, but it was the proof that these tools worked and that we had access to the electronic timescale to see what happens in molecules. Then the next thing was to do, okay, hydrogen is nice, but it's not probably the most interesting molecule for chemistry. And so we went further and took phenylalanine. Repeated the same experiment, same kind of glasses from the third side. And here's the movie that you get when you do these calculations by using the actual Attosecond process of the experiment. And the interesting thing here is you see two colors. This is the electron density, the whole density, and you see different colors. So the purple means excess of charge with respect to the average charge that you have in the catalyst. And the other color is the opposite. And as you can see, there is an alternance of colors around a given functional group. For instance, here around the NH2 group, the amino group, sometimes this is yellow, sometimes it's purple, which means that sometimes it has more charge than it should have, sometimes it has less charge than it should have. And you are a real chemist, not a theoretical chemist, as most of us. You would not accept this. Because for a chemist, the amino group should always be an electron donor system. So it should have less charge, in general, than the rest. Well, this is true, but not always. Sometimes it's just the opposite. And that means that if you are able to develop tools in the lab that can do something to this molecule when the charge is in the wrong place, then the chemistry really will be absolutely different to the normal chemistry that people are used to. And this is not because of our imagination. This reflects in the real experiment in which ions are recorded as a function of the delay between the pump and the probe. Then you see some oscillations here, and the period of these oscillations coincides precisely with the period of the oscillations of charge that we see here. So this has been experimentally confirmed. And it's not only phenylalanine. Same experiment, same modeling was performed for tryptophan, same conclusions. So electrodynamics to generate with an attosecond pulse can be very complicated and can be completely counterintuitive from the chemical point of view. So more recently, we were interested in seeing if we could provide some useful information for donor acceptor molecules, which is very important for optoelectronic applications, for instance, solar cells, etc. And we took this molecule, which is, spananitranilene, and what I have plotted here is as one of the most elementary processes that is used in organic chemistry textbooks to describe electron transfer. And here, if you go to these textbooks, you will see that the NH2 end here can give an electron to the benzene ring here, producing a double bond, and then you get this. And this, as a result of that, you have an electron more here, an electron less here. This is in all textbooks. So what we wanted to do is just to put a number on top of the arrow. How long does it take? Well, what you're going to see here is a movie of the electron density again, as a function of time. Okay, and I want you to focus around the amino group because it's important group here in this study. And what you will see here, these green and red colors represent the charge around the lone pair of the amino group. And this green thing is the charge around the carbon-nitrogen bond. Okay, it's precisely this region over here. Now you look at this, you see that there's less and less charge around in the lone pair, then goes to the carbon-nitrogen bond, and then it cuts back, but in the other side. And if you focus your attention on this, you will see that the structure of the NH2 group is changing. Initially, it is pyramidal, and sometime later it becomes completely plane. This is necessary to produce a double bond here. You have to change the hybridization from sp3 to sp2. Again, this is an organic chemistry textbook. Here you can see better how the charge varies in this region around the lone pair and around the carbon bond. You see that the change in charges of the other one atomic unit of the charge. So it is huge. So this picture is correct. There is a full electron going from here to there. A full electron. And what we could estimate from our calculations is that it takes 10 femtoseconds. So this is also the time that the system needs to change the hybridization from sp3 to sp2. And this is confirmed by the experiments performed in Milan. You see that there is a rise, rapid rise, as a function of time, and it reaches the maximum at around 10 femtoseconds, which is when we have the maximum transfer of charge. So this can be useful in chemistry, okay? And so that's why I think it's important to go in this direction. Let me mention very briefly, to avoid going to taking too much time, this using a single attosecond pulse is complicated because, as we have seen at the beginning of the talk, what is produced in the lab is a train of attosecond pulses. So actually, what is easy to do in the lab is to use the full train of attosecond pulses in combination with another pulse that is the probe pulse. This is easier experimentally, but complicates the interpretation, complicates the analysis, but since it's easier, more people do this kind of experiment. So, in fact, pan-prof experiments, as the ones I showed you, they are very few. Nowadays, there are like 10, no more than that, since 2010. While in this scenario, there are hundreds. So I will just show one. There is also one of them simply because Anne was involved in it. We were also involved in interpreting this, and I will not go into the details. I only want to mention that in this particular experiment, what they were able to measure and we were able to calculate is how long the electron takes to escape from the nitrogen bond when you shine it, release it to the left. And we did it in the vicinity of a shape resonance that lies in the continuum. And the result is that it takes 70 attoseconds, in good agreement with the theory. So ionization is very fast, okay? Even though we are looking at the shape resonance where ionization should take longer, which means that, in normal conditions, ionization takes on the other a few attoseconds, very few attoseconds. But this time scale can be measured and described there. New directions. This is the status where we are nowadays. Where do we want to go with this? Well, the ideal experiment would be to perform attosecond pump, attosecond probe. I didn't say anything, but you read it in the slide for sure. We were using an attosecond pulse to start the dynamics in the system. And we were using a probe pulse that was this red pulse I showed, and you read probably 6 or 15 femtosecond duration. So it's not the ideal pulse. Why people use this infrared pulse to probe the system? Because since you already have an infrared pulse in your lab, because you use this to produce the attosecond pulses, well, instead to throwing it to the garbage, you recycle it in some way, and you reuse it to use it as a probe. So it saves money, it saves space, and it avoids a big problem, which is the fact that attosecond pulses are very weak in intensity. As I said at the beginning, this process of harmonic generation is very inefficient. So very few photons are produced, which means that the intensity of these attosecond pulses is very low. Now, if you start with a pulse of very low intensity, and you use as a probe another pulse of very low intensity, then most likely what you will see in your experiment is noise. Nothing. So people use infrared pulses to probe the system because they were more intense. But this is not the ideal tool because they are too long. So the ideal experiment is to use 2 attosecond pulses. This cannot be done with current high harmonic generation sources, but can be done by using pulses generated in free electron lasers. And I will now describe what is it. It has nothing to do with the methodology I told you, the one related to high harmonic generation. It's based on accelerator physics, so you have a long accelerator of electrons that obliges the electrons to go through an undulator, as you can see here. And as a result of this, these electrons emit light in the XUV and the X-rays. And this light is emitted only for a few femtoseconds or less than 1 femtosecond. And the main advantage of this is that the intensity of these attosecond pulses is of the order of 10 times orders of magnitude larger than that provided by high harmonic generation sources. So this is a possible direction for the future, and people are working on that. The only problem is that you want to perform an experiment in a facility like this. There are 5 in the world nowadays working, only 5. You have to apply for big time, be very lucky to get it, and be very lucky that the lasers are stable enough to see something. So it's not an experiment you can do. You cannot offer this as a topic for a PhD thesis, let's say, because you would kill the student. Not only one, but several generations would kill. But this will arrive. Now, the other problem that is intrinsic to this field is that since high harmonic generation produces attosecond pulses in the XUV or the X-rays, you always ionize. So for many years, personally, I have tried to convince chemists about the interest of this field, and I failed always, because chemistry is not about ionized molecules. We always have neutral molecules in the solution, or in that spectrum, we want neutral. So the question is, Could we use attosecond pulses in the visible or UV regions where we don't ionize the molecules? Well, you should take something into account. If you go down to the visible, for instance, red color, green color, things like that, then you realize that the period of one oscillation is about 1 femtosecond. So you cannot go beyond 1 femtosecond, because if you go beyond 1 femtosecond, you don't even have a single oscillation. If you don't have an oscillation, you don't have light. You have something probably extremely interesting, but it's not one. You need an oscillation at least. So, well, you will say, well, but maybe we can produce pulses of 2 or 3 femtoseconds. This will not be useful to study dynamics in the hydrogen molecule because it's very small and it takes, too short. But if you are interested in studying molecules of chemical interest, which are usually big, this is more than enough. Because if it is big, the electron transfer will take ages to go from one end of the molecule to the other one. Ages means tens of femtoseconds or even more. And with this, you have the resolution. So a new direction is to perform this kind of experiments to use UV visible pulse of 2-3 femtoseconds combined with an attosecond pulse just to take the pictures at different times. And this is difficult to produce, but it has been recently realized by 2 experimental groups, among them the group of Mauro Nisoli in Milano, who participates in this project that we bought, and we want to mention it, but I think it's important to mention that, and this is the messages, this combines the expertise of an experimentalist in quantum optics and laser physics, so knowledge about atoms and molecules, an organic chemist making synthesis in the lab, the real one, okay, and a theoretician. I think it's the way to go on in the future in this field. This cannot belong to the definite field. Now, all this is very now finishing. After this long talk, you may say, oh, yeah, it's very interesting. You can even do attosecond science without ionizing the molecules, and you can improve the statistical measurement by using free electron lasers. But do we see the electronic motion really? No, I was cheating you for 45 minutes. The only motion you saw is this one, this one. This comes from theory. What comes from experiment is this. Some oscillations there, some fringes here that change of color. You need glasses to understand that. But theory is limited. Theory can provide glasses for systems that are not too big. So if you want to use this for very big systems, you would like to perform an experiment in which you really see the movie directly in the experiment. Is there any tool in the lab that allows you to see the electron density with your own eyes, without any help from theory? Yes, there is. And it exists since a long time ago. By the way, this also was a topic that allowed some people to get the Nobel Prize, the developers of the scanning tunneling microscope. So with the scanning tunneling microscope, you can see the electron density of the molecules. This is a TCNT molecule, and what you can see here, this is what, of course, there are hundreds of papers, okay, about this. I took this because I was part of this, so it was easier for me to put an image. And also because it's super nice, because you can see the electron density associated to different molecular orbitals of this molecule, HOMO, LUMO, etc. So STM images can really provide you an image, a direct image of electron density. And this is the theory just to show that this is not just an artifact, it's what it is. So the question is then, is there any possibility to combine STM with attosecond science? Well, this question was asked by a lot of people since the very beginning of the field, but it has been solved only in 2022. This is an experiment performed in Stuttgart in the group of Klaus-Kern, and we were participating also to combine the theory in which they deposited, these monsters. For me, this is a monster. This molecule is called PCTA. And then they put this on a gold substrate. This is the STM tip, and they use a combination of two pulses, and they vary the delay between them with attosecond distribution. And this is the movie they got. Not so nice as the ones I showed before, because this is a very complicated experiment. But what is showing here, you see that there are two kinds of molecules. This is totally covered by molecules. And then you see that sometimes the density is located in one half of the molecules and later on it moves to the other half. So, you know, there's motion of electron density from one half of the molecules to the other half of the molecule, and you can resolve it in time. And this is the theory movie. That, of course, looks nicer. It has two. But basically, says the same. So there is the capability nowadays to look at the electron density directly and see how this electron density changes in real time in the attosecond times. With this, I will conclude. The main conclusion is that now with it's very light pulses of this attosecond relation, we are able to see electrons moving in molecules, and we are starting to control this motion by using different kinds of attosecond pulses. But this is a topic that will require a whole talk. And don't forget that studying the electronic motion is the essence of physics and chemistry, but also biology. So where we can go, I don't know, but I think it's worth performing these studies because we may find surprises in our way. If you want to know more, you are a specialist on this, I recommend you to go to this chemical review paper we published a few years ago. If you are not familiar with this and you don't speak English very well, you can read this paper I published also a few years ago in Investigating Química. It's in Spanish. It's a very elementary thing, so you will understand this better. And of course, I had to quote all the people here. Here I put the people who have been involved in all the theoretical results I have shown. Okay, not everybody in the group. As you can see, most of them are no longer in our university, in different places. Some people came back to my department. Some other people came back to a different department, like this one, which is the Department of Chemical Physics, Applied Physics. So I think this shows that, you know, this field is really productive for something, giving people opportunities to find jobs in different places. Of course, apart from people, we need money. And I have to acknowledge the funding provided by these agencies, without which this work would have been possible. Just this is the very last slide. If you really like this, or you think that this could be interesting for you, there is a workshop that we organize in Tenerife Island at the end of February, beginning of March, which is attochemistry. Okay, and the important thing here is not that it's in Tenerife, but registration is free, no registration fee, so €0. You only have to buy a plane ticket, which is around 100 euros, and life in Tenerife, and La Laguna in particular, in February is super cheap. Nobody goes there, it's low season. So you want to spend €300, 350, you have the whole congress with the best specialists in the world talking about this. Thank you very much for the attention.
Thank you very much, Fernando. Clear and very didactic talk. So now it's time to ask any questions.
I know students are always afraid of asking questions, but I encourage you to ask questions. As I said, students have the advantage they are not contaminated by their supervisors yet. So they may ask questions that we never ask ourselves because we have a lot of experience. And these are not the right questions to ask because they are not original. So please go ahead.
Yeah. Can we solve the exchange correlation energy with these methods so we can develop the density function theory and obtain like the
I see you come from DFT world.
yeah.
Exchange correlation. I got it. Okay, let me put it this way. Density functional theory is useless. but KCF also. Okay, if you want to describe the electron in the continuum, which is what you have to do. Now, if you are able to describe the electron in the continuum, what is left behind, yeah, that is a molecular catalog. And for this, you can use density functional theory. For instance, if the molecule is very large, okay? Or if the molecule is smaller, then you can use KCF, KCF2, all this kind of theory. So for the remaining molecular catalog, you can. So what is the exchange and correlation functional we use? A standard one, because you should not forget that although the electron is ionized, it's still interacting with the remaining electrons. And nobody knows how this function should look like. So you have to try and see if it's okay. So we can test this by comparing, for instance, what we do before doing these expensive calculations, we compare with photoionization spectra that are measured in synchrotron radiation facilities, which is old-fashioned research, which I don't think is correct to say it's great, but it's absolutely necessary to have very accurate measurements of the photoelectron spectrum. And then if your description of this exchange correlation function is correct, you should get good agreement with this measurement. Then you are sure that you are describing correctly the system. And therefore, you can use this to make a complicated calculation that need to be done to describe all these things happening in the Attosecond chemistry. So there is absolutely no experience on this. So the one we are using, if I remember correctly, is LB94.
More questions? I have a question, Fernando. You mentioned at the very beginning of the paper, you are dealing with the efficiency of the higher generation. So I'm wondering, what's the typical medium they use for higher generation? And is there any way or any trends in the field to think about media that can produce higher efficiency for the generation of this process?
You need higher energies.
Higher energies.
Yes, of course. I mean, there's whole community working on that. So basically, these experiments were performed in argon. Argon is very popular, super popular system, but noble gases in general, because you want to have a chamber with these gases or noble gases. So basically, they use neon and argon. That's the still nowadays. But those noble gases have produced harmonics only in the H2. Now, you want to go to the X-rays. What you do, you still use argon in them. But what you do is, instead of using mid-infrared light to produce the harmonics, which has this 1.5 femtosecond period, you use mid-infrared light, which have much longer period. So the wavelength is much longer. So let's say if instead of 1.5 seconds, you have something of 3 second duration, this means that the traveling time of the electron, since it escapes from the neon or the argon, is increased. It will not be 1.5 femtoseconds, it will be 3 femtoseconds or more. The longer the excursion, the higher the kinetic energy they acquire. And then when they come back and leave this excess energy, they leave more energy because they have more kinetic energy. So people are generating attosecond pulses by using high harmonic generation, not by changing the gas, but by changing the wavelength of the light that is used to generate. So typically mid-infrared. And people who are doing this in Spain is, for instance, the ICFO, the group of James Picker, is doing this among others. It's not only him, there are many people doing this. Still, the problem is that these pulses are super weak. The intensity is super low. So they cannot compete with the free electron lasers at all. But what you know, they have other advantages. Phase stabilized, etc. too technical for it.
More questions? Don't be afraid. Come on.
Have you been any successful attempts to take advantage of this new chemistry that the Attosecond predicts, or is there advances in that direction?
Well, I hope we
No, so that's the thing.
I hope we'll be able to find something because we got a lot of money.
No,
this no, so far, I mean, the most advanced thing we did is what I showed at one of the slides, is just to realize that, you know, this process of charge transfer from one donor group to the rest of the molecule takes 10 minutes. Now, what we want to do, I'm revealing this part because I know nobody's going to measure this, it's impossible. If you don't have the process, you can't do it. And you don't have the theoretical tools either, so I have no problem sharing. so, I mean, the idea we have is, and that's why they gave us money for this. I mean, paraneutrality was just the benchmark. What we want to do is to study more extended systems, like the ones you have in optoelectronic devices or solar cells. And just first to visualize these dynamics, and then shape the attosecond pulse in such a way that we modify the natural electron dynamics. Why we want to do that? Because as you all know, the efficiency of these processes is very low. The solar cells you put in the roof of your house have an efficiency of 15, 16, 17%. So that means most of the sunlight is lost. So there are many approaches in the market to try to solve this. Most of them focus on longer time scale. What we want to see is that we can generate a completely different charge transfer from the very beginning that will help us to improve the efficiency. So this is what we are working. So I hope that in 5 years, when this project will be finished, if you invite me again, I will answer the question.
Okay, more questions? Yeah.
Thank you so much for your talk. I enjoyed it very much. I wonder, in the case of the simple electron transfer for the amine, benzo, nickel groups, what happens with the amine group? It goes from the non-plane to plane, but what about the rotation? Does it rotate in the process?
I mean, at this time scale, it doesn't have time to rotate. Rotation takes much longer. Picoseconds is too slow. Picosecond is a million times longer than an attosecond. Yeah, of course, there is rotation, but all this occurs without any rotation because it takes much longer. So there might be interesting rotational effects, yes, but at much longer time scale.
But not involved with the electron transfer?
No, it's much faster. Much faster. By the time the molecule wants to change the orientation, the transfer is finished. Not only that, but this pyramidization and planarization of the amino group, you know, it's over, it's finished.
I was told that Fernando is actually actively working towards biomedical applications with this Attosecond laser. So,
Yeah.
do you know what, more or less what
Well,
the prospect is?
Well, I will tell you what he says, and then I will tell you my opinion. So probably are different. Ferenc Krauss is a master. What he did in those experiments is incredible. Okay? Very possible. This was done in 2000. Now, what he's now saying is what, I mean, he gave a talk precisely about this in this Nobel Symposium. So after his talk, all of us thought this guy is not going to get the Nobel Prize because of that talk. Basically, what he claims is that by using attosecond pulses, he shines, I mean, they take blood from patients, and apparently, when they shine this blood, which is prepared in some way, it's not just the raw blood and it's treated with something that I don't remember, and then they send these pulses, and then they look at the absorption of this blood. And so apparently, empirically, it's totally empirical, what he says is, when there is some compounds that are associated to tumors, lung tumors, there is a shift in the position of some peaks that can be related to the presence of these compounds that are associated with those tumors. What he claimed is that he had performed an assay in sample of 1,000 people, of course with hospitals and so on and so forth. 1,000 had tumors, another 1,000 didn't have tumors, and they were doing this, and he claims that, yeah, this shift in the position of those peaks is significant. From what he showed, it's very difficult to say. And also, I'm not saying that this is not possible. Maybe it's possible. Why attosecond pulses? Maybe you don't need attosecond pulses for that. That's my main thinking. And in fact, well, I mean, he was interviewed in El País journal, and of course the journalist was fascinated by this. It seems to be very, very useful, and all the interview was about this. Well, I think it's good to go on in this direction to see what happens. But my impression is that you don't need attosecond pulses for that. You need probably to rely not for attosecond duration. And secondly, well, we are still very far away from any real application. And even if it is at the end, it is confirmed that it's useful, well, this is not going to solve liver cancer, and it's just a diagnosis tool that apparently is more sensitive than any other diagnosis tool. So this is what he's doing. So when he finished this, I think people are exploring applications. So I think it's good that people explore things that may seem crazy, because sometimes you find things that are really important. But I would say that most of the people in that room were rather skeptical about this, maybe because there were not many young people around. And you have already your own story. And
Any other
I don't
questions?
know.
No more questions? Okay, so let's thank Fernando.